This is the second part of the video on heats of reaction and Hess's law. In the first video we covered learning target number 14 there, using Hess's law to calculate the enthalpy change during a chemical reaction. In this video we'll look at these next two. The first of which is we want to be able to write chemical equations for what we call the standard heat of formation of a substance. So standard heat of formation, and do notice how we use symbols for that. Instead of an Rx in for reaction, we have the subscript F there. It's still an enthalpy change, so it's still delta H. And then anytime you see this superscript 0 here, that means we are at standard value. Okay, if you see that, it kind of looks like a degree sign. That means we're at standard value, and we'll talk about what that means here in the definition, which is coming up here. So a standard heat of formation is this. It is the change in enthalpy, so it's still delta H, that occurs during the formation of 1 mole of a compound in its standard state, meaning what would it look like, what physical state would it be in at 25 degrees Celsius and 1 atmosphere of pressure. That's what we mean by standard state, and it forms from its elements in their standard states. So let's just take a look at an example of this to help you understand this definition. Our example will be for the formation of sulfur trioxide. And the reason we call this a standard heat of formation is we're always talking about forming compounds, and they get formed from their elements. So when we write this equation, we are going to form 1 mole of SO3, sulfur trioxide. Note that's in our definition here, during the formation of 1 mole of a compound. So when we write the equation for this reaction, 1 mole of SO3 will be formed, and it's going to be created from sulfur and oxygen, because that's what sulfur trioxide is made of. So those two are the reactants. So when we write the equation, we put those elements, sulfur and oxygen, as the reactants. And notice the standard state of sulfur is a solid, and you may not have known that, and that's all right. But if we had sulfur at 25 degrees Celsius and 1 atmosphere, it would be a solid. Oxygen is a gas at 25 degrees Celsius and 1 atmosphere, and my guess is we're pretty familiar with that. Notice it is O2 because it's diatomic. That's its standard state. Oxygen does not exist as individual elements, as we've learned before. And notice the balancing here. I have 1 mole of sulfur because I have 1 mole of sulfur on my product side. And then for my oxygen, I have 3/2 of a mole of O2. Well, that would be 3 moles. 3/2 times 2 would be 3. Because over here, you'll notice we have 3 oxygens, SO3. And then notice we have SO3 gas because that is the standard state of SO3 at 25 degrees Celsius and 1 atmosphere. And if we were to look this up, and this is what you would do, you would look this up as far as what this value was. You would see it has a value of negative 396 kilojoules, or it might be written as negative 396 kilojoules per mole, because it's always for every 1 mole of substance that is formed. Now, one thing that will come up will be the standard heat of formation for an individual element. For example, if I wanted to know the standard heat of formation for sulfur, you might say, well, what's the reaction going to be? What's it made from? Well, it's just sulfur, so it's made from sulfur. And as it turns out, that any element in its standard state, its standard heat of formation is just 0. And you can see that on the chart that you guys have that I gave you in class. You can see some individual elements there, and they're always listed as being 0. All right. So let's see some examples in practice here. So I have 3 different compounds here. I asked you to write an equation for the standard heat of formation for each of them. So pause the video, try it. If you need some help, if you're not sure, go ahead and play the video. Maybe watch the first example and then try the next 2. Alright, so for this first one here, we have nitrogen monoxide, and as we discussed from the last slide, we always form 1 mole of it. So it's not about having to figure out what the balancing is to figure out that it's going to be 1. It's always going to be 1. So I have 1 mole of nitrogen monoxide, and you can see here it's in the gas state, so I have that notation there. And then I ask myself, what elements make it up? Well, it's nitrogen and oxygen. So I have nitrogen, which is diatomic, so it's N2. And because I need 1 mole of it, notice there's only 1 over here, I need 1/2 of a mole of N2. So that will balance the nitrogen. And then I have oxygen, same story there, that's diatomic. and so I need half of a mole of that. And notice both of these are in the gas state, because as we know, nitrogen and oxygen, standard states would be gases. Alright, next one there we have Fe3O4. And again, like we have said, it's always for 1 mole that's produced. So you can see there's a 1 there. And we're told it's a solid, so I have that notation. And then it's made of 2 elements, iron and oxygen. Iron, well, as we know, if we just had iron, it would be a solid, so Fe solid. And there's 3 moles of it, so I can balance with the 3 moles over here on the product side. And then oxygen, as we know it's a gas, I would need 2 moles of O2 to give me 4 moles of oxygen in total, because I have 4 on the right side. And then the last one here we have, that would be phosphoric acid, H3PO4. We can see it's dissolved in water, aqueous, so I can see I have that in my notation here. And there's nothing I need to do differently with that. Sometimes you'll see that aqueous and say, well, how do I deal with that over here on the reactant side? There's nothing different you need to do. Just ask yourself, what is the standard state of the elements that make it up? So we have hydrogen, and as we know, hydrogen is diatomic, so H2. And I need 3/2 of a mole of it, because that would give me 3 moles in total. 3/2 times 2 would be 3 to give me 3 moles of hydrogen. Phosphorus, you may not know that that's a solid in its standard state. That's all right. You can look at that chart I gave you. If it's on there, you can see that it would be a solid, although I'm looking at that chart right now, and I don't think just phosphorus is on there. We can look it up too. It's not something I would expect you to just know, though. So if you have a question about something like that, please just ask. And then for oxygen, we do know that's a gas in standard state. And I need 2 moles of it because it's diatomic, so 2 times 2 is 4 to match with the 4 moles over here on the product side. Alright, so we have seen how to write chemical equations for the standard heat of formation of a substance. We now want to combine what we've learned from that and from our Hess's Law learning from the previous video to use the summation equation to determine a standard heat of reaction. Alright, so Hess's Law and standard heats of formation or standard heats of reaction. So let's revisit this reaction here. This is the first one we looked at in the last video, where we said if we tried to do this experiment, actually do the reaction to measure its enthalpy change, it wouldn't do us a whole lot of good, because most of what we get actually is not SO3. And so we use Hess's Law to determine an enthalpy change, a heat of reaction. Well, now I'm asking for a standard heat of reaction, meaning what if we did this reaction, we did it at 25 degrees Celsius, we did it at 1 atmospheric pressure, what would the enthalpy change be there? Well, if we combine what we know about Hess's Law with what we just worked with those standard heats of formation, we can simply use those tables of heats of formation values to calculate this without having to do a whole bunch of equation manipulation. And here's how we do that. So if we're looking for a standard heat of reaction, Hess's Law can be simplified. And it can be simplified as such, where a standard heat of reaction, and again notice the subscript symbol there, the little letter O. I wish I could put it over here right next to the H, but the formatting won't let me do that. But if I'm looking for a standard value, we can use what we call the summation equation. And this equation here is the summation equation, where we take the sum of, and recall from your math classes, and if you haven't had it yet, this is a very simple idea. This symbol here, the Greek letter sigma, always means a summation, where we add up what comes next. So we add up the heats of formation, the standard heats of formation of the products, so what's on the right side of the equation, and we subtract the sum of the standard heats of formation of the reactants, what's on the left side of the equation. So if we apply that idea to this particular reaction, it would look like this. And I know this notation looks a little hairy, but I'll explain it here to help you out. So my products here is only one product, that's my 2 moles of sulfur trioxide. So I'm going to take 2 moles, because there are 2 moles of it, times the standard heat of formation. You see that symbol there, the delta HF with the standard symbol there. The standard heat of formation of sulfur trioxide gas. And that's something you would just look up on a table. You do nothing to calculate. You just look it up on the table, or it'd be given to you in the problem. That's what I do there. So 2 moles times that standard heat of formation of sulfur trioxide gas. And then I'm going to subtract out my reactants. And so I subtract out 2 moles, because there's 2 moles of sulfur, times the standard heat of formation of sulfur solid, minus, because again it's a reactant, I want to subtract out all the reactants, minus 3 moles, because there are 3 moles here in the equation, 3 moles times the standard heat of formation of oxygen gas. So if I look up those values, and if you look at the table you were given in class, you will find those on there. If I look up those values, this is what you'll see. The standard heat of formation of sulfur trioxide gas is a negative 396 kilojoules per mole. Do notice they are per mole values, and as we talked about from the previous slides, it's because these standard heats of formation are always forming 1 mole of product, so it's kilojoules per mole. And then for the sulfur solid and the oxygen gas, those are both 0, and you'll see those on the table, but you actually wouldn't need to look those up because those are both elements, individual elements, in their standard state. Sulfur is a solid, oxygen is a gas, oxygen is diatomic, so O2. So those are both 0 kilojoules per mole. So as this turns out, all this one is, because when I multiply by 0, it just turns into 0. All this one ends up being is the 2 moles times the negative 396 kilojoules per mole, and that will give you negative 792 kilojoules. Notice moles would cancel there, 1 to the numerator, 1 to the denominator, so we'd get kilojoules. If you compare that to what we got from yesterday's video with Hess's law and manipulating the equations, we also got negative 792 there as well. And the reason they're the same is those enthalpy change values that I gave you yesterday were actually the standard values, the same ones that we're using here, and that's why we get the same thing. So you can see how Hess's law, if we're looking for a standard heat of formation, can be more easily applied with this summation equation. So to summarize here, the summation equation tells us that the standard heat of reaction for a reaction, again this notation there at the superscript 0 there, means we're talking about a standard, is just the sum of the heats of the standard heats of formation of the products minus the sum of the standard heats of formation of the reactants. Alright, let's see a couple more examples in practice here. So what I've done here is I've given you an equation. Actually, I have 2 of them here, so 2 different problems. And I asked you to calculate the standard heat of reaction, so what we just did, for each reaction using the summation equation. So I would encourage you to pause the video, give it a shot yourself. If you need to play it and get some help, do that. Alright, this first one here, we're going to use the summation equation as we're told. So from the previous slide, we know that's the standard heat of formation of the products minus the standard heat of formation of the reactants. So when I look at my equation, I can see I have 4 moles of nitrogen dioxide and 6 moles of liquid water. And so to start, I will have 4 moles times the standard heat of formation of nitrogen dioxide gas plus 6 moles times the standard heat of formation of liquid water. Do pay close attention to the physical states, because if you look at your table, you'll see some of these substances, water I know for sure, is listed with multiple states, and not just liquid water that's on there, but also solid water, which we call ice, and water in the gas state, which we call water vapor. So make sure you get the right one there. And then I also have 2 reactants, so I'm going to subtract out those. So minus 4 moles times the heat of formation of ammonia, that's NH3 gas, and then minus the 7 moles of the standard heat of formation of oxygen gas. So if you look those values up on the table, you will see these numbers. For the standard heat of formation of NO2 gas, it's a positive 33.2 kilojoules per mole. And then for the liquid water, that's a negative 285.8 kilojoules per mole. For the ammonia gas, that's a negative 45.9 kilojoules per mole. And for the oxygen, because that's in its standard state, O2 gas, that's 0. And so if you plug all that in your calculator, it should give you negative 1398.4 kilojoules. And if we were to apply Hess's law, if we were given the reactions with these same standard heats of formation, we would also find that we get the same thing applying Hess's law and manipulating the equations. Alright, take a look at the next one here. And before we go any further with the next one, I will tell you that this particular substance, this would be propanoic acid, that is not on that heat of formation table that I gave you. So when we get to that in the problem, I just give you the value. And that's the case with anything. If there's something that's not on that table, I will just give that to you. Again, you don't need to memorize the stuff. It will just be given to you. Alright, so applying the same equation here, we can see our products. We have 4 moles of carbon dioxide and 4 moles of liquid water. So 4 moles times the standard heat of formation of carbon dioxide gas, plus, this should say plus here. I'm not sure if I did the math right then. I might have. This should be a plus sign here because I'm adding the 4 moles of the water because it's a product. So plus 4 moles of 4 moles of the liquid water, the standard heat of formation. And now I'll subtract my reactants. 1 mole of the standard heat of formation for the propanoic acid. Again, that's the one that's not on that table. And then, because it's also a reactant, minus the 5 moles of the standard heat of formation of oxygen gas. So if you look up those values, or in the case of the propanoic acid, I'll just give that one to you. That's the negative 534 kilojoules per mole. You should see this, and it looks like I did do the math right here. I do add that 4 moles of the water, liquid water, because it's a product. You should get negative 2183 kilojoules. Alright, so to summarize here, we've written chemical equations to show the standard heats of formation of a substance, and we've also seen the summation equation to determine a standard heat of reaction.